Hello everyone. First of all, I would like to thank Ida for this invitation. Today I will present my work on contactless sensor for long-term vital sign monitoring in ambient assisted living environment. I'm working under the supervision of Professor Bassam Abdulrazak. Okay, my outline for today will include overview, background about non-intrusive sleep monitoring as well as non-intrusive vital sign monitoring. Also, it will include related work about the sleep monitoring as well as vital sign monitoring. I will also discuss about our proposed methodology. Then we talk about results and discussion. Finally, we'll give some recommendation. Okay, first of all, what is the hypothesis behind our work? In fact, vital signs, in particular heart rate as well as respiratory rate, can be measured non-intrusively using a pressure sensor which can be placed under the bed mattress. We have done several contributions in a particular area. First of all, we have made a non-intrusive system for measuring vital signs, including heart rate, breathing rate, and body movement. Also, we propose a system for measuring sleep quality. For measuring sleep quality, we take into consideration several parameters. These parameters include wake-up time, bedtime, time in bed, sleep interruption, by getting information about the frequent body movement and bed exit events. Finally, we have done some work regarding sleep apnea detection. I will explain it later in detail, but in some sleep apnea, we have to differentiate between normal breathing and abnormal breathing. What is the motivation? In fact, we need a long-term monitoring system that can measure vital signs for days or weeks. Unfortunately, we cannot achieve that at hospitals. Also, the number of seniors are increasing dramatically in recent years. The load on caregivers are also increasing to monitor the vital signs manually, and current methods to monitor the sleep quality are fairly bulky and expensive. In a different way, they cannot be used as home-based devices. To give an example, the gold standard approach for measuring sleep is called polysomnography. The polysomnography is an overnight sleep study that has to be performed in a specialized sleep lab. The polysomnography study involves several parameters. For example, the heart rate, respiratory rate, oxygen saturation, the SpO2, eye and leg movement, body position, snoring, and brain waves. The patient has to sleep in a lab for at least 8 hours to monitor the sleep function. It is quite complicated, very expensive, and it cannot be transferred to home environment. Now, I will consider how can we measure the sleep, or what are the current approaches in existing market to measure sleep quality. We differentiate between these approaches in two different ways. First of all, we consider the wearable sleep trackers, and later we discuss about the non-wearable sleep trackers, which is the subject of my presentation today. Most of the companies in the market are claiming to measure sleep stages that involves differentiating between rapid eye movement sleep and non-rapid eye movement sleep. In fact, this cannot be done using a wearable device because we have to measure the EEG, or the electrical activity of the brain. Also, they claim to measure sleep quality smart alarm. Smart alarm is a function, or it is a feature which can wake up a patient or a subject only during light sleep. Also, they claim to measure vital sign, in particular heart rate. What are the advantages of the wearable sleep trackers? The wearable sleep tracker can provide continuous and long-term data collection. However, they overestimate the total sleep time and also the sleep efficiency. Also, they underestimate the wake-up time after the onset of sleep. And one of the main limitations of the wearable sleep trackers, specifically for the seniors, they might actually cause skin irritation. So we consider such trackers not suitable or non-convenient for the seniors. The second category we discussed today is the non-wearable sleep trackers. The one also the companies more or less share the same characteristics. They claim to measure sleep stages, sleep quality, smart alarm, vital signs. The pros or the advantages of the non-wearable sleep trackers, they can provide long-term data collection. They are quite convenient for the seniors because we simply can place the sleep tracker under the bed mattress, so we don't have any kind of contact with the senior. The disadvantages of the non-wearable sleep trackers, they are quite sensitive to motion artifacts, in particular those originated due to body movement or because of the presence of a bed partner. Now we will discuss about the common framework to analyze the data acquired from non-wearable sleep trackers. The idea of the non-wearable sleep trackers is to place the sensor under, for example, a bed mattress, or it can be placed under the seat of a chair. The outcome or the output of the non-wearable sleep trackers is a kind of a composite signal. This composite signal include what is called ballistocardiogram, the mechanical activity of the heart. They also include respiratory signal, the movement of the chest and abdomen. Also, they include the overall body movement. In order to process such composite signal, we need to apply a pre-processing step to get each individual signal separately. And also we have to remove motion artifacts and the bed exit events. After detecting the informative signal out of the composite signal, we have to apply a signal separation. The concept of the signal separation is to apply a band-pass filter with cutoff frequencies which can equivalent to the vital sign of interest to obtain the respiratory signal and the cardiac signal. After obtaining both signals, we apply different algorithms to determine the heart rate and the respiratory rate. In the literature, there are several ways to measure the heart rate. One of them could be peak detection. We can also use wavelet analysis, power spectrum analysis, or what is called clustering-based analysis. The respiratory rate also can be measured using a peak detector or a power spectrum analysis. The most important signal out of the non-wearable sleep trackers is called ballistocardiography. The ballistocardiography, in fact, it measures the mechanical activity of the heart when the blood is ejected or pumped out of ventricles to the large blood vessel. The typical shape of a BCG signal contains several peaks. For example, the HIJKLM. IJK is called the ejection phase of the cardiac cycle. Most of the approaches in literature are trying to find the J peak because the J peak here corresponding to the R peak in the ECG signal. I would say the IJK is a cardiac cycle we need to detect in order to determine the heart rate. In fact, this figure is an ensemble plot of this core BCG signal. Here we just give us some summary for the different approaches in literature to detect heart rate. We differentiate the methods in literature into different domains. The first one is the time domain approaches. For the time domain approaches, the idea is to detect the local maxima or local minima using a sliding time window. This approach is very sensitive to motion artifacts, and most of the approaches are tested in a controlled environment, so we exclude such approach from our analysis. The second approach is the frequency domain approaches. The idea of the frequency domain approaches is to find the dominant peak or the dominant frequency in a particular frequency range using, for example, the capestrum or the short-time fast Fourier transform. The issue or the disadvantage of the fast Fourier transform or the capestrum, the peak in the spectrum may get wider and multiple peaks may appear. And also, most of the approaches are tested in a controlled environment. So we also exclude the frequency approaches from our analysis. One of the best approaches or the optimal approaches for analyzing the BCG signal is the wavelet analysis. The idea of the wavelet analysis is to decompose the signal into different components. they call wavelet and detail component. Then we select the component that shows a match with the cardiac cycle. The pros of the wavelet analysis, they are suitable for analyzing the non-linear and non-stationary signal. In a different way, they have the capability of the multi-resolution analysis. Lastly, the clustering-based analysis. The idea of the clustering-based analysis is to build a model using machine learning approaches or the convolutional neural network for the heartbeat shape. However, the limitation of the clustering-based approaches is the manual labeling. The manual labeling is quite a restrictive property. The training step here should be repeated whenever the data collection protocol has been changed. I would say the shape of the signal, in particular the ballistocardiogram, can change between and within subjects. It is quite different than the electrocardiogram. So the application of convolutional neural network will be limited, and further investigation into such particular problem has to be done. Now I will discuss about our selected sensor. In our application, we use a microband fiber optic sensor. The idea or the concept of the microband fiber optic sensor is based on light intensity modulation. So if we apply a pressure to the sensor mat, the light intensity in the multi-mode fiber changes according to the ballistic forces on the heart. Then we can modulate the outcome as a respiratory signal as well as cardiac signal. Figure 6 shows a longitudinal cross-section of the microband fiber optic sensor. Figure 7 gives an example of the real deployed sensor in our application. The dimension of the sensor is 50 by 20 by 0.5 centimeter. It's quite actually convenient, and it can be placed under the bed mattress, or also nowadays we are using this sensor in a mobile application to test its efficacy if we can measure vital signs during, for example, exercises. So far we have presented our proposed sensor. In our application, we have validated the sensor in 3 different domains. The first domain is the health and wellness application. In this application, we collected data from 50 subjects while they are resting in a massage chair. In the second application, which is a clinical application, we collected data from 10 patients during a polysomnography study. And at last, we have deployed the system in a real-life deployment, and we collected data from 3 senior female residents for over a month. In the very first application, we were interested to detect heart rate. In the second application, for the clinical trial, we detected heart rate, respiratory rate, as well as apneas. For the last application, the real-life deployment, we were able to detect heart rate, respiratory rate, as well as sleep quality. This is a general framework we are using to detect the vital sign of interest. First of all, we have the fiber optic data. We apply a pre-processing step to remove the body movement, the bed exit events. The output of this step is 3 signals. Either a sleep signal where we can detect the vital signs, or bed empty. Bed empty means no one is on the bed. Bed motion means someone is on the bed. However, the amount of artifacts are quite large so that we cannot determine the heart rate. After we detect the sleep signal, we apply, as we discussed previously, the source separation. The source separation is nothing but a bandpass filter, and the cutoff frequencies of the bandpass filter is equivalent to each individual signal. After we get the ballistocardiogram signal or the cardiac signal, we apply the wavelet decomposition. Out of the wavelet decomposition, we choose the force level response coefficient because it shows a match with the cardiac cycle. Then, using a big detector, we can determine the heart rate. For the respiratory signal, first of all, because there is a trend in the signal, we have to subtract a third-order polynomial fit from the respiratory signal. Then we apply a smoothing filter. After all, we detect the local peak using a local peak detector. Now I will explain the pre-processing step. Actually, we are using a statistical method to determine the 3 signals. The idea is to divide the signal into equal slices and the length of each slice is 10 seconds. Since the sampling frequency of our sensor is 50 Hz, the length of each slice is 500 samples. After dividing the signal into equal slices of 500 samples, we determine the standard deviation of each slice. Then we sort all the standard deviation in an array, and we compute the mean absolute deviation of the standard deviation array. If it happens that any standard deviation was greater than twice the mean absolute deviation, we consider this particular slice as a body movement. In fact, it happens that during such incidents, the amount of motion are quite large so that no vital sign can be detected. And if the standard deviation was below a predetermined threshold, in our case is 15 millivolt, we consider no one on the bed. Actually, it is provided by the manufacturer because there is always current in the multimode fiber optic. And if the standard deviation was in between these two thresholds, we consider it as a sleep signal. After determining the sleep signal, we apply the wavelet decomposition. We choose what is called maximal overlap discrete wavelet transform because it is time invariant and it can be applied to any size of the signal. It shouldn't be of a power of 2 like the typical wavelet actually. The idea of the wavelet is to apply a series of filters to the signal to obtain wavelet component as well as detail component. Here is an example of a 3-level wavelet decomposition. After all, we are only interested in either the detail component or the smooth component. This is an example of a 10-second BCD signal, as we can see here. After we apply the wavelet decomposition, in this case, we apply 4 decomposition levels. As we can see, the 4th level smooth coefficient shows a match with the G peak of the BCG signal, so that we decided to choose the 4th level smooth coefficient to determine the heart rate. For comparison, we use the capacitor analysis. The capacitor analysis is just the inverse discrete Fourier transform of the log magnitude of the discrete Fourier transform of a signal. The idea here is to look for the maximum peak within a typical frequency range equivalent to the heart rate. In this figure, for example, the heart rate happens at 1.02 second, which is equivalent to 61 beat per minute. We just multiply the 1.02 by 60 to obtain the beat per minute. Furthermore, we use the autocorrelation function as a way of comparison. The autocorrelation just measures the degree of similarity between a signal and its lagged version of itself, actually. The idea is quite simple. We just find the maximum peak within a typical frequency range. Here we only display the positive part of the autocorrelation function. Now, after we described how we measure the heart rate, we now describe how we measure the respiratory rate as well as the apnea. As we discussed previously, we need to remove the nonlinear trend. In order to remove the nonlinear trend, we subtract the respiratory signal from a third-order polynomial fit. Then we apply a signal smoothing. We use Savitsky-Golay filter. Then, using a peak detector, we can find the respiratory rate. For the sleep apnea detection, we applied an adaptive histogram-based thresholding to discriminate between apneic events and events. What is apnea? Apnea is a complete closure in the upper airway. However, hypopnea, for example here, is a reduction in the airflow. Most of the people who have apnea are snoring, and they have quite disturbing time to sleep. The bed partner is the one who can detect early actually the presence of the sleep apnea. As I told previously, the gold standard approach to measure the sleep quality is the polysomnography. However, we were trying here to provide, I would say, an assistive tool using our microband fiber optic sensor to measure the sleep apnea. Our sensor only is only a single channel sensor. However, the polysomnography is multiple sensors. Now I will discuss about how we collected data in the first application in our choice, which is health and wellness application. The idea of this application was quite interesting. We have placed the microband fiber optic sensor behind the headrest of a person sitting in a massage chair while he was or she was playing some games. In fact, it was a session during stress relief massage. We collected the data locally, then we send it to a remote server for data processing. In this particular application, the quality of the signal was quite disturbed because we have some time where there is no contact between the head of the person and the fiber optic mat. Also, during the movement of the chair, the signal quality was quite low. Now, we compared our proposed approach using the wavelet analysis with the what is called SIMDAN is an empirical mode decomposition method. It is quite similar to the wavelet. However, it has a very high execution time. So for real-time application, it cannot be used. Also, since there are several mother wavelets, we need to select the optimal wavelet for the heart rate detection. We tried the Dabochi, the Simless, the Coeflet, bi-orthogonal wavelet, as well as the reverse bi-orthogonal wavelet. As we can see, the bi-orthogonal 3.9 achieved the lowest mean absolute error comparing to the other mother wavelets. At the same time, the complete ensemble empirical mode decomposition, or the SIMDAN, achieve a lower mean absolute error compared to the wavelet analysis. However, as I mentioned, the computational time for the SIMDAN algorithm is quite high, so it cannot be used for real-time application. Since we decided that we will use the bi-orthogonal 3.9 mother wavelet, we tested the efficacy of such mother wavelet against the autocorrelation function, capistrum, and fast Fourier transform. As we can see, the mean absolute error using the Fourier transform is very, very high. It's 29 beat per minute. For the capistrum, it was 58.3 beat per minute. For the autocorrelation function, it was 76.54. Those values cannot be considered as clinically approved. So we have excluded this method from our analysis, and we have decided to use the wavelet analysis because it gives, I would say, a reasonably good results, 10.12 with a standard deviation 4.69. For the second application, which is the clinical trial, we recruited 10 patients who have obstructive sleep apnea. To determine the severity of the obstructive sleep apnea, we have to measure what is called apnea-hypopnea index. The apnea-hypopnea index is the total number of apnea and hypopnea per hour of sleep. If the apnea-hypopnea index was less than 5, we consider the patient as normal. If the apnea-hypopnea index was greater than 5 and less than 15, it's mild. If the apnea hypopnea, if it was greater than 5 and less than 15, it's moderate. If it was more than 15, if it is greater than 15 and less than 30, it's moderate. If it is greater than 30, you consider it as severe apnea. In our case, we have some patient with moderate apnea and we have some other patient with severe apnea. Here is an example of a typical BCG signal. As we can see in the first row, the gray signal is the raw signal obtained by the sensor. The red line here represents the respiratory signal. As we can see, the respiratory signal is nothing but a low-pass filter version of the raw signal. In the second row, the gray signal is the ballistocardiogram, and the red is the force level smooth coefficient. As we can see, the local maxima of the force level smooth coefficient shows a match with the cardiac cycle here. Here I will explain the results for our apnea detection. As I mentioned, for apnea detection, we used what is called adaptive histogram-based thresholding approach. In order to determine the apnea, we used two different windows. One window with a size of 60 seconds and the second window of a size of 30 seconds. If we consider the window of 60 seconds, we can see for patients with less severe apnea, the sensitivity actually increases exponentially. For example, if we consider patient 5321, the sensitivity increases exponentially for 46, 51, 62, 71. However, for the patient with very severe apnea, the sensitivity decreases exponentially from 78, 76, 51. For patient 6, although it has a moderate actually apnea, the number of what is called central apnea was quite high. The central apnea is different than the hypopnea and the obstructive apnea because it happens from the brain. So the shape of the signal is quite typical to the normal breathing. So the system failed to detect such events. What is interesting in these results is our system is suitable for patients with less severe obstructive sleep apnea. And this configuration is helpful to detect obstructive sleep apnea early and to avoid further complication. Why I'm saying so? Because if the patient already have severe obstructive sleep apnea, we cannot intervene and it has to go for surgery. Or the doctor has to prescribe the CPAP to help him to breathe normally. However, if we are able to detect apnea early for patients with less severe apnea, we can provide an early detection system. We have preferred the sliding time window of 60 seconds over the 30 seconds because we found out for one of the patients, the p-value was 0.12. So in the different way, all the p-value using the 60-second time window was in the normal range actually. This figure actually shows the annotation provided by our system and the annotation provided by the gold standard approach. The first row provided the apneic annotation by the polysomnography, and in this case, the estimated EHI was 36.8, and our system was able to detect the apnea-hypopnea index such as 23. Now we move to the last application, which is a real-life deployment. Here at the AMI lab, we don't only collect data from the sleep sensor, we have other sensors like the motion sensor, the contact sensor. So after collecting this data, we have the gateway in our case, which is a Raspberry Pi. In fact, there are several research opportunities here, in particular, people who are interested to work in interoperability. So if someone are actually keen to collaborate with us, he is quite open to talk with us here. However, my area of research, I will mainly consider the bit sensor here. For the real-life deployment, we collected data from 3 female residents. Here, we collected a kind of survey before the data collection, when they sleep, when they wake up, and the nap time, okay? Of course, reported time here is approximate. Patient reported no chronic diseases or disabilities. The first female resident sleep on the floor on a bamboo mat. So we place the fiber optic mat under the sleeping rug or the bamboo mat. The second resident sleep in a double bed, but she always sleep on one side of the bed. The third resident sleep on a single bed. As we can see, the mat has a very large size. So we tested the capacity of the mat in different conditions here. This figure actually is very interesting because it shows the output of our sensor, the output of the sensor previously used to detect the sleep, and also the survey. This first row shows the output of our proposed sensor. The green rectangles show the time where the patient was supposed to sleep. The red rectangles show the time where there is a body movement. The blank shows the time where no one was in the bed. Here, for example, as we can see, the resident here sleeps probably between 9 to 10 p.m. and he wakes up around 7 a.m. The result is quite consistent with the survey, because here we see the wake-up time is quite, the bedtime is quite the same, the wake-up time is quite the same. However, using the motion sensor to detect the episode of sleep was not very accurate. The orange or the pink color detects the time where there was a body activity, or we assume a bedroom activity here as the person was on the bed actually. It was not necessarily true. So the accuracy of the sleep mat is more accurate than the motion sensor. Here we discuss the results for the second resident. According to the survey, the resident used to wake up at around 7 a.m. However, on Wednesday, she used to wake up at 4 a.m. We have constructed a planned ultimate plot with three limits of agreement: the upper limit of agreement, the lower limit of agreement, and the mean. Here, we were able to detect that the resident on average wakes up around 7, which is quite okay with the wake-up time. And also, we were able to detect that the wake-up time on Wednesday was around 4:30, which also agree with the survey. For the third senior, the result was quite interesting to us, because we were able to detect that the senior used to wake up at around 3 a.m. in the morning. We thought in the very beginning that our system has some failure. However, when we discussed with the resident, she confirmed that she wake up at around 2:30 or 3 a.m. in the morning to practice some kind of religious practices. Also, our system is able to detect the nap time. Here we present the results for the third resident. According to the survey, the resident used to sleep 2 to 3 times between 1 p.m. and 3 p.m. Each time the nap was around 30 minutes. Also, our system was able to detect the start and the end of each napping time. And on average, we determined that this particular resident used to have nap time for around 1 hour and a half. One of the most important feature also which we are able to detect is the time in bed. Time in bed here means the time when the resident sleeps or stay on the bed, and the time when the resident leaves the bed. The first and third seniors or resident have on average a time in bed around 9 hours. However, the second senior have a time in bed more than 12. We actually discussed with this senior because it's quite high, and we have a lot of boys even reach 17. When we discuss it with this senior, he say, I used to sleep on the bed or rest on the bed and watching TV for a long time. So we advise him to change his sleep habit. This figure actually shows a distribution for the sleep disturbances. The sleep disturbances here include the body movement and also the time where the senior get out of the bed, for example, to go to the toilet. We use a moving time window of 3 days. The orange line here is the upper limit of agreement. The blue is the lower limit of agreement, and the red is the moving average actually. As we can see, most of the time or most of the points are within the 2 limit of agreement. So it is quite normal that the patient or the senior has disturbance sleep. Any one of us can move frequently during the night actually. It's quite normal. The most important is that all the points here are between the 2 limit of agreement and we don't have any outliers. Now we describe the heart rate detected at each day. This figure actually is the box plots of the heart rate for the first resident for each day of the deployment. The red line here is the median. Why we use the median? We use the median to determine any trend over time. It's quite normal to see outliers because we detect the heart rate for all the day using a time window of 30 seconds. But when we see that the trend is not that much, so we consider the resident have a typical vital sign, which is the case actually. They don't report any cardiovascular problems. Also, we were able to determine the trend in the respiratory signal over time. Now I come to the conclusion. As I mentioned, we were able to test our system in two different environments, health and wellness application, where the data were collected during a stress relief massage. Also, we were able to test our system in a clinical trial, where the data were collected from 10 patients. As we said, the system were able to achieve close results with references devices here. But again, the limitation of the contactless sensor is that it cannot provide a continuous vital sign monitoring, because once the patient or the user is out of the bed, we cannot have any information about vital sign. So if we want to provide continuous vital sign monitoring, we have to use wearable sensor, for example, the Fitbit. To enhance or improve our results for the sleep apnea detection, we are planning to use a different sensor like the finger pulse oximeter, which measures the oxygen saturation to get more accurate information. Also, as a future work, we are planning to detect heart rhythm problems, in particular arrhythmias or atrial fibrillation. It is quite important application that can help actually physicians or doctor before and after the surgery. Thank you for your attention. Any questions?
Thank you very much, Ibrahim. It was a very interesting presentation. So we have questions for Ibrahim. Okay, I do have a few questions. So my first question will be, I think, very naive because I don't have expertise at all in the subject that you presented. I just wanted to know, can you explain what is the difference actually in the treatment of the signal for the detection of the respiratory rate versus the treatment of the signal for the detection of the heart rate? What are the main differences?
Okay. For the respiratory rate, actually, the shape of the signal is quite simple. If we use a very typical peak detector, we can detect the respiratory cycles, the inhalation and exhalation. However, for the cardiac signal, it is quite complicated because the shape of the signal does not have a consistent distribution. So we need to use a method that can decompose the signal into meaningful components. In our case, we use the wavelet analysis. The wavelet analysis enables us to decompose the raw data, which is the gray here signal, into multiple components. I come here. Okay. Yes, for example, this is a BCG signal. It looks simple, but in reality, you cannot even differentiate between the cardiac cycle and the typical peaks. Here, I just give a simple example to show you where the cardiac cycles. All the maximum peak here are considered as cardiac cycle. To determine the cardiac cycle, we apply the wavelet analysis. Here we use a wavelet analysis with 4-level decomposition. So we have 4 detailed component and 1 smooth component. The smooth component here, each local maxima correspond. So if we apply a big detector, we can easily detect the cardiac cycle. That is the answer, yes.
Okay, yeah, thank you very much. So most of the tool would actually be best at detecting the respiratory rates than the heart rates, right?
Respiratory rate for normal people is easy to detect. However, for people with sleep apnea, detecting respiratory rate is quite a issue actually, because the shape of the signal becomes more complicated. The apnea itself affects the morphology of the signal.
Okay.
Yeah.
Okay, I understand. So another question, but I just wanted to ask: are there other questions from?
So what?
Are there other questions for Ibrahim?
Okay.
No? Okay. So my second question, you showed that comparison of your method, your contactless method with the result of using motion sensors, right?
Yes.
So
Okay.
I was wondering, do you have comparisons of your results, for instance, with the detection using wearable devices?
So far, we don't have it, but I can confirm. Okay, if we use a smartwatch, detecting the sleep will be quite okay, and the result will be actually even more accurate than our system, because you have a direct contact with the skin. And the idea of the wearable devices like smartwatches, they detect the heart rate, and also they are able to detect. In our case, we wanted to remove any complication to the patient. So our objective is to find, I would say, less intrusive system as possible.
Okay.
But the wearable sensor would provide actually accurate results as well.
Okay.
Yeah.
So you showed the comparison. So are there studies in which actually that study actually how to combine all these different tools together in order to be the less invasive possible?
Most of the studies in literature, people are either using non-contact sensor or contact sensors. They don't actually combine both results. But some people actually are using, I would say, an accelerometer along with the sleep mat as an indicator for motion artifacts to reduce the impact of motion artifacts.
Okay, very interesting.
Because the wearable sensor like the smartwatch and our proposed sensor, more or less, they are detecting the same information. For redundancy, yes, we can do that.
Okay, because I guess it would allow to have results that are.
That's definitely true.
Right.
But again, you need to consider the target group you are dealing with.
Okay.
If you are dealing with patient with Alzheimer, for example, with cognitive decline, simply they will remove the smartwatch actually, or it's quite complicated actually. So you need to be less intrusive as possible.
Okay.
Yeah.
Okay, very interesting. So thank you for your answers.
Thanks.
Are there other questions for Ibrahim? Well, if there are no more questions, we will thank you. So I just want to remember to recall everyone that the presentation is recorded and will be on the department website. If you have other questions for Ibrahim, you can just write to him.
Yes.
To ask your question, and you can also see the video that will be on the department website.
Okay, thanks a lot.
Thank you very much.
Thanks.
And see you next week. Bye.
Thanks. Bye.